All right. Hello, everyone. I think there are a couple of people that we have on today that haven't been in these sessions yet. So as always, I'd like to open it up for introductions at the beginning. I think HJ, I don't think you've been here yet. Would you like to introduce yourself?
Yeah. So I'm HJ, and I've been involved with RChain since 2015, and yeah, I've been building the bounty system, and with Dan Connolly and James Carver and Kit Blake. And Peter Point is also pretty active at the moment. So yeah, and I'm following this new technology, and yeah, it's quite interesting. It's a world changer. So
cool, awesome, glad to have you. Anyone else? I see we have Jeremy Beal. Have you been here before? Would you like to introduce yourself? You're on mute. Yeah, Jeremy, you're muted. Okay, yeah, no problem. And then we have someone who's called in on phone as well. I don't know who that is. Would you like to introduce yourself?
it's gone.
Oh, okay. I guess not. Sorry. Also,
Thank you. You guys hear me now?
Oh yeah, we can hear you now.
All right, perfect. Hey, so my name is Jeremy Bill. I've been with RChain for about a month and a half now. Just to give you a brief background, I just recently graduated just over a year ago in software development. And right now I'm working with RChain doing market research and content creation. So I pretty much take a lot of the technical documents and I make it into a regurgitable, that's what I'm looking for. I guess I put everything technical in like layman's terms so everyone can understand, especially as like a new dev. So if they wanted to migrate to RChain, they can like learn about row calc and rolling and then like an easy like transition into it.
Okay, awesome, cool. Glad to have you here. That's an important perspective to have and one that I have as well. And yeah, I also just want to make it clear that if I ever call on anyone to introduce themselves and they don't want to, that's a totally acceptable answer. And if you've talked to me before and you don't even want me to ask that question, I'll do that. So, okay, awesome. With that, let's get started. Let me share my screen here. Sorry. Here we go. So last week, or on Monday in Greg's class, we talked about the notions of bisimulation a little bit. And then also, or mainly our focus was sort of on fully abstract encodings of one language into another. So I wanted to give a little bit of background into what bisimulation is. This is sort of the place where I got stuck the first time through the PyCalculus paper, and finally on this reintroduction to it, I think I'm able to explain it better. So I'm hoping to present that to you. And also, if there are any questions along the way, I'd like to hear those. And then I guess after we go through these things, then we can talk about the numerals example or the numerals exercise that Greg gave. So first, before we understand the notion of bisimulation, we need to understand the notion of observability. So, and for all of these examples here, I'm using row calculus. There's a similar notion for the PyCalculus, for the ambient process calculus. For all of these, observability and bisimulation are pretty common things to define when you're defining process calculi. So an observation relation is symbolized by the down arrow with an n after it. It's parameterized by a set of names n. So to have an observation relation, you are talking about a grouping of names. So you're talking about observation on a grouping of names. And it is the smallest relation that satisfies those below equations. And what those below equations say is that if we have a name that is in our set N, or structurally, or name equivalent to a name in our set N, then if we have X output some process, we call that name observable at X. Any questions there? This is I think one of the most important things that we'll talk about today. So I want to make sure that this is clear. So an observation relationship parameterized by a set of names, and if you have a name in that set, if you have a process that is sending on a name in that set, it is called observable at that name.
So question, can that also be, and I'm taking this installed in the same context of Bisimulation, correct?
Of Bisimulation what?
Where you can, so sorry, it's kind of loud, I'm at a coffee shop, but long story short, so is this like in relation to Bisimulation to where you observe the events that that name is carrying out? Does that make any sense?
Yeah, yep. So we'll get there. So yeah, this is like, yeah, really important to Bisimulation, but we haven't defined Bisimulation yet. Yeah, but yeah, good forward thinking there. That is going to come into play. So and then I guess the second equation down here is saying that if we have some process that's name observable at X, putting it in par with another process, that new combined process is still going to be name observable at X. Okay, and then we will write P is, I'll say is eventually name observable at X. That's sort of my terminology, but it's symbolized by this double down arrow here, and this means that if we there we go. Got to refresh the page. So if we have a process Q such that P eventually reduces to Q, and Q is name observable at X, then we'll say that P is eventually name observable at X. So that means if we have a process that reduces in some form, then and that new process, that's the reduction, is observable at X, then we say that P is eventually observable at X. So this gives us a way to talk about not only what is observable at a process right now, but what is observable at all possible reductions of a process. So here's a couple of examples. Let's do true or false. Is X output P in parallel with X input Y dot Q? And then I have saying that N here, is it observable at of the notion of observability where N is the set X, Y, and Z, so all of the names here. Is this process observable at X?
So if all the small notion of X, Y, and Z is observable at Q, can X use that as a process?
Sorry, with that noise, I couldn't quite hear you.
Sorry, so loud. So you're saying that can the observable processes at Q, which is X, Y, and Z, be recorded on X, like in parallel?
No, so,
like,
so
I guess that processes?
Okay, so what I'm asking is this process on the left, that is these two processes running in parallel, but this itself is a whole process, is this process observable at the name X? And X is in our set on which we're looking for observable things. So we can use the definitions up here. So we know that x is in our set here, right? That's the first thing, because we have, here's our set, and x is in our set. So we have this condition, and then and so this is y. Yeah, so x is in our set, and x is name equivalent to itself. So we have those conditions. So now we can check to see if this is true. So are we outputting something on x? Then we would be observable at x. And the answer is yes. Right here, we are outputting something on x. So this whole process is observable at x.
And do we need y and z in this set, observable set?
Nope. We're just saying that we're observing the set x, y, z. For all of these examples, I think we're observing the set x, y, z.
But we only need x.
They are what?
In this case. We only need x in this case to be in the set. Yep,
exactly.
Okay, thanks.
Okay, so we'll go to the next one. Yeah, so is this process observable at x?
Yes, I think.
Okay.
Yep.
How come?
X and y are in the set.
Yep, x and y are in the set. Are we sending?
Yeah, but it is not the same, right? Yeah. X and y is not the same process.
Nope, that's the receive process. Yep.
I mean, the x receiving and the y sending must be name equivalent, right? Oh yeah, but they are in the set. Yeah, they are in the set.
So what we're saying is that we have one process that's listening on x, and will bind what it receives to y in process P, and we have another process that's sending something on y, namely the process Q. And what we're asking is this whole thing observable at x? So
I would say yeah.
Yeah. So the answer is no, because we are not sending anything on x here. So it is name observable at y because we're sending something at y, but it is not observable at x. This is an important distinction, that in the row calculus, in the row calculus, our input guarded processes are not observable. They're not in our notion of observation. So listening on a name does not count as observation as observable at that name. Only sending on a name counts as observable at that name. Is that understandable?
Can you show the first presentation again?
This one? Or that?
Yeah, that's the one.
Yep. So x output is the only thing that is observable. We have nothing that talks about input.
Okay.
And here.
Okay, got it.
Yep. So in the pi calculus, observability is tied to the notion of send and receive, but in the row calculus it's not, because this is an asynchronous calculus.
So in your first example, this receiving side was not important.
Nope. Yep.
In this example.
Yep. This is not important at all.
Okay. Thanks.
Okay. So we did that example. All right. Here is another example. So is this process observable at X?
Yeah.
Right, because we're sending something on X right here.
It's also observable of Y, right?
It is not observable at Y because this output on Y is not going to happen and cannot happen until we've received something on the name X, right? And it's definitely not observable at Y because Y is going to be, this Y could be another name. This is a bound name in this process. So we will eventually, if we've received a message on X, it's actually going to be eventually observable at Z, I think, right? Because this can reduce with this, receive on X and ascend on X. We're sending the name Z on X. And so now Y will be replaced with Z in this process. So it's actually eventually observable at Z.
Oh, got it. Yes. Y is an bound name, right?
Yeah, Y is a
Y.
bound name. So even if Y was not bound, though, even if Y was not bound, it's not going to be observable. This process is not observable here because this input hasn't happened. Because we cannot send anything like this until we've received an input.
Okay, cool.
Okay, here is another.
One question.
Yeah.
When you say first this process must receive something, you're referring to there must be another reduction, and that's the thing that must happen.
Yes, a reduction must happen before yeah, this takes place, and specifically a reduction that that has this as the input, that is receiving on X and sending on X for this process. So it's not any reduction that has to happen. Specifically, we have to, this process here that's highlighted needs to receive an input.
Okay, thanks.
Okay, here is another example. Is this observable at Y? So, yeah.
No.
Yep, so that's what we were just talking about. So yep, that's not observable at Y. What about this process? Is this process observable at Y?
No.
Yep, no. So even though that this name isn't bound, yep, it's still not observable at Y. We just talked about that. Now, is this process observable at Z?
No.
Right? It's not. We're not sending on Z. Now, is this process eventually observable at Z?
Eventually, yes.
Yeah. We just went over that as well.
Yeah.
Cool.
Yeah.
Those are all the examples that I have for observability. Are there any questions there? Or what questions do you have there? Okay. Let's move on then. So bisimulation is going to use this notion of observability. So we have an n-barbed bisimulation is parametric in a set of names n. This set of names we are going to use for our observability set of names. So we will say that P is n-barbed bisimilar to Q if P reduces to P prime, or P being n-barbed bisimilar to Q implies that if P reduces to P prime and Q eventually reduces to Q prime, or if P reduces to P prime, then q eventually reduces to some q prime such that p prime is n-barbed bisimilar to q prime. This means that if we have a reduction in p that is observable at some set of names, then we will then our process q will eventually reduce to some form such that p prime and q prime are both observable at the same set of names. So yeah, so we need this one down here. So if p is observable at x, then q is eventually observable at x. So what we're saying we're doing here is that we are looking at a set of names for which our processes are bisimilar, and we are going to examine really closely for that set of names what the outputs to those names look like, and if we sort of send messages on the same channels, or if we can send messages at the same channels for all the forms of our reductions, then we will call those things as simulations, or simulating each other. The other important notion is that it's a symmetric binary relationship. So P being bisimilar to Q is true if and only if Q is bisimilar to P.
If you replace the fat arrow and the other arrow, is it hold also? Or I mean, is this the normal error, like a smaller number of reductions than the eventually?
So the larger arrow could be just one reduction. Is that what you're asking?
Yeah, you said they are symmetric, so probably you can just reverse the direction and it will still be hold.
Yeah. So right, if
you said that the difference between these two arrows, the fat arrows is eventually.
Yeah. So are you saying that if I put the fat arrow here, and then the skinny arrow here? I don't think that's true, because it's not the case that if if P eventually reduces to some P prime, then Q needs to be able to reduce to that same form in only one step. So if we replace P with Q here, if we swapped around for every place that we have P's, we have Q's, this says the same thing. Or yeah, if this was Q and this was P and this was Q and this was P, then this equation would still be true. Then yeah.
Because from my understanding, as long as they match like sequentially, like going down, then that's all that should really matter, correct? So yeah, like you just said, it doesn't matter whether or not the arrow swaps to P or the other arrow swaps to Q. As long as they both match sequentially, is that all that matters? Does that make sense?
No, I guess I'm not really understanding what you mean by matching sequentially.
As I understood, it's like someone observation and have eventually observation, it's true. But if eventually observation, it's not observation.
Yeah. Yes. Okay, so yeah, these arrows, right, yeah. So if P is observable at X, you said that right. Well, let's move on to some examples, and then we can come back if this isn't making sense. Okay, so true or false. We have the set x, y here, which we are looking at to view bisimilarity. And we have some x, which is sending the name y. And we have some x that is sending the name z. Are these two processes bisimilar?
I think yes, because we're sending and y.
Yeah.
Yeah. Yeah.
So it doesn't actually matter that we're sending two different things. These two processes are bisimilar. Actually, oh wait. Yeah, that's also kind of a silly example because we don't have any reductions here.
Yes.
Yeah. So yeah, I should have made that example a bit better. But yeah, there are no reductions there. Let's move on to ones that.
But
Shoot. Yeah, these examples aren't great. Now that I'm reading this. Yeah, sorry, my examples are not good. Let's see, what was I trying to get at though?
So we need like a sending and receiving, and after they're both receive, this is like a final.
Yeah, so let's we're gonna have to use our imagination a bit on these examples, and so, but I think what we'll need to do for all of these examples is for the left process, imagine that this is in the process context of something that is listening on X and then doing nothing, and then the nil process. And then the same thing over here. We need something in parallel with this that is listening on X and then just throwing whatever value it gets away. Yeah. Yep. So we'll need to have.
So in this case, both sides are reducing to listening, to listening process.
Yep. So in both cases, these things will reduce to 0.
Oh.
The null process.
Oh yeah. Because one is receiving, one sending, and this was reduced to 0.
Yep. But we do have this observability. Oh, so actually no, this is okay. We don't need to. I'm sorry. Yeah, I guess we don't really have any examples where we like look at all the reductions on the one side. We're just sort of using the top level, so there could probably be more in-depth examples, but I think these examples are still okay, because if P is observable at X, then Q needs to be observable at X, and that's sort of eventually observable at X. And this is the condition that I'm mostly focusing on here. And then you can just sort of understand that if P reduces, then yeah, and since it's a, yeah, okay, I think the examples are okay. Sorry about that. Okay, so are these two processes equivalent under this binary symmetric relationship, or this bisimulation relationship?
Yes.
I think it's observable on Y, but not observable at X.
So, so which process are you talking about? Because there's a process on the left-hand side and right-hand side now. So this process is observable at both Y and X, and this process is just observable at X. So the answer is that they are not bisimilar. And that is because that is because it's a binary symmetric relationship, right? So that means that for this to be true, this has to be symmetric to this, and this has to be symmetric to this. And we are asking ourselves for observability, for bisimilarity across a set of names that includes both X and Y. So if we are sending on X on or sending on Y on one side, and we are not sending on Y on another side, those processes are not bisimilar.
And if Y is not in the set, is this also okay, or?
Yep, so I think that's my next example here. So in my next example, we have Z, where Z is not in the set. And the answer is yes, these two processes are bisimilar, because we don't care about sends on Z. That's not in our but yeah, those aren't that's not in the set of names that we're caring about simulation over. Okay. Here is another.
So Jay, can you go back just a second?
Yeah.
So it's okay that Y is in the set, but it's not observable at Y.
Yes. Yeah. So it's just saying that it's not saying that all of our processes need to be observable at all of the that our process needs to be observable at all of the names in our set. It's just saying that when it is, when process P is observable at some name, then Q has to be eventually observable at that name.
Thanks.
So here is another one.
I think they are the same.
Yeah. Yep. This statement is true. Sorry. Yeah. Go ahead. Explain.
No, only because of sending on X.
Mm-hmm. Yep. This doesn't matter because this isn't observable. So we can add those in there, and they don't reduce. So if they reduce to things, if there was another process part in here that sent something on Y, then those would not be bisimilar.
And this is what you mean by eventually reduces.
Yes, exactly.
Oh, great, thanks.
So right, here's another one. You might have to look at this one for a little bit, but I'll give you some time.
No, they're not.
No, yeah.
I think they are. Because they both are observable on X, or at least the right-hand side is eventually observable on X, I think.
Where do you see it?
I think that's, if I follow it right. So if you look at the right-hand side, X is going to be sent over Z, so to carry that over the par. And so so Z is now X. So replace the next send on Z is now an send on X. And so that makes it observable. If I have that right. That's what I think.
Yep. So, and what about this send on Z here? Do we care about that? Do we care that this process is observable at Z?
No.
No.
Why not?
Because it's not a set of names.
Yes, it's not in the set of names we're looking at. So yes, these two processes are bounded by similar.
If you had a receiving on X on the left side, do we reduce this process or not? Because X is on the set of names.
If we have a receive on X over here,
Yeah.
instead of a send,
Or no, in par.
Okay. If we have a receive on X in par, then
I think he's saying that if you had a par there, what the COM rule would reduce it down to perhaps nothing.
Yeah, let's just say nil. So
Yeah,
it depends on what your continuation is after the receive. It depends on what you do after the receive. But say we just grab something from the input and then don't do anything, or maybe we grab something from the input and then we wait on another name, and we input guard that process as well, then yeah, that doesn't change these two processes being bounded by similar. Okay, any questions about bounded by similarity? Or what questions do you have about bounded by similarity? So I guess the cool thing about this notion of bounded by similarity is that there are a bunch of ways that we can talk about two processes sort of like exhibiting equivalent behavior, or one process being able to simulate another process. So this is apparently a pretty strong way to talk about process simulations or process equivalences, and that there are a whole bunch of other notions. If you read the Pi calculus paper, you'll note that, let's see, let's find it here. So the Pi calculus paper that calls these a whole bunch of process congruences, I think. So it's after abstraction and concretion. Yeah. Yeah, okay, equivalence, congruence. So
yeah, I do wonder too that what's the motivation for wanting to be able to make these statements about processes.
Yeah, yeah. We might be able to go over that a little bit here. I have an idea, but I haven't read far enough to see these things being used to maybe give the best answer that I possibly could. But yeah, so we'll see in the Pi calculus paper here, right? We have this notion of strong reduction equivalence, which requires that Q isn't eventually observable, or Q doesn't eventually reduce and have the same observabilities. It's just that the reductions are strict. There can't be any reductions in between. If P reduces to P prime, then Q also has to reduce to Q prime, and all of the names that are observable at both at P prime have to be observable at Q prime, and P at Q. And then there's there's also the notion of the weak reduction equivalence. And this is more similar to the notion that we just talked about with this, that has this, instead of the double arrows here, they use the arrow star. So this has the eventually notion built into it. So yeah. So I guess one of the reasons that we want this notion of bounded by similarity is that what we want to be able to do is we want to be able to examine a new type of process calculus And we want to see if we have any enhanced expressive power in our new calculus. So what we can do is we can try to write down essentially a translation from our higher order, or from not our higher order, from our new process calculus into whatever process calculus we're checking expressive power against. And so this is done in Greg's RoCalc paper, right? So we talk about encoding replication and encoding these other operators that one might want to add to the row calculus to make it look more like the pi calculus. And essentially Greg says that these aren't necessary because if with those encodings, you can take a calculus that has those new productions in it. You can encode, you can translate statements made in that calculus to the row calculus, and those statements that are now in the row calculus are and it can be done in a way that is fully abstract. That is a full abstraction, and this full abstraction notion will contain. So we'll talk about full abstraction in a second here, but the full abstraction definition will contain within inside of it this notion of barbed bisimilarity of two processes. I hope that helps explain the motivation. But let's talk about what a full abstraction in a language is first for a little bit. So a full abstraction is parametric in two equivalences. So we need an equivalence in our source language, and we need an equivalence in our target language. And our target language is a full abstraction. Yeah, actually, I don't know if I said that right. I don't know if it's target language is a full abstraction of source language, or source is a full abstraction of target. Actually, it shouldn't matter because it's an if and only if. So our source language is a full abstraction of our target language if and we've defined our two symmetries. Those are given to us as parameters of this full abstraction type. And so if P is equivalent under some notion of equivalence in the source language to Q, then the translation of P is equivalent in some other notion of equivalence in our target language to the translation of Q. And so if this is true, if we can take, if this statement is true, then we've said that we have a full abstraction, and that you know that we don't have any jump of expressive power between our source and target languages. If we can prove that this isn't true, we can prove that we have, or since you can prove, you can talk about these equivalences arbitrarily. You know, you need some sort of meaningful notion of equivalence, and bisimulation is what a lot of people use. But you know, you can talk about or quantize or sort of narrow down exactly what the jump of expressive power is between your source and target languages if you can find cases where this isn't true for certain equivalences.
Jake, could I just throw out some sort of intuitive thing?
Yeah, great.
So like our assignment from Greg was to capture the decimal numbers.
Mm-hmm.
So that forms a language, I guess we could say. So if we just took a different base, like base 2, could we say that, okay, well, these are equivalencies because you can express the same, they have the same expressiveness because you can get to the same numbers, base 2, base 10, base anything. Would that be something fair to say?
Yeah, I think so.
But this can be different if we choose different equivalents. For example, alpha equivalence or structural equivalence.
Yeah, so that was what I asked Greg as well, and you know, he pushed back a little bit on the notion of alpha equivalence and structural equivalence being sort of meaningful equivalences through which you you evaluate these things, because they really are more talking about the structure of the language itself and the grammatical structure of the language, and not so much about the semantics and about like what an execution actually means. So structural equivalence sort of like gets us at this notion of these processes are built to be the same, whereas bisimulation brings us to the this notion of like, you know, we can right, like we did back here in this example, right? We can say that we have something that listens on a separate name that we don't care, that's outside of the set of the names that we care about in our bisimulation, and is going to sort of synchronize across that name to simulate our process on the left. And that these are the types of things we might want to do to encode different types of operators, like the choice operator, for example, being encoded in the input guarded choice operator being encoded into the row calculus depends on, you know, adding. I'm pretty sure depends on adding these new names on which you are receiving things, and then executing code to decide which choice you're making. So, and that, you know, this wouldn't be allowed in structural equivalence. But yeah, but yes, you are right in that, you know, you could use, like, it's totally legal to use the notion of structural equivalence on one of these sides. It's just not that meaningful, because we have this better notion of simulation.
I think it's now it's like a little clearer, but yeah, thanks.
Yeah. I'm still struggling with these notions a lot as well. So yeah, Okay. Cool. I guess with that, we could go into some quick discussion about the numerals assignment and how both myself or Tomislav sort of like went about it or are thinking about it initially, or we could just call it there. I don't know. What's the thoughts?
Oh, I would like to hear your interpretation.
All right, fair enough. I'd also love to hear yours. Okay. So here is some code that is not complete and a bit ugly. So the way that I approach this is I said, okay, I want to encode the numerals. I'm going to start with just the basics. Let's just say we have a grammar that all you can do is write a single-digit number in it, right? So I'm, you know, here's our grammar construction. Is digit equals 0 or 1 or 2, ... you know, up to 9 or whatever base number you're talking about is going to be different. So then I just defined case objects. Don't worry about these other things in here for now. Case objects that that represented each one of those digits. And then I said, okay, so now we need some way of pushing these things together so that we can have a number that's more than one digit. And so instead of just like adding that to my grammar, I actually created a new grammar that is parametric in this notion of digit or some object. And what I'm saying is that our numeral can either be a single digit number, is still okay, or we can push two numerals together. We can concatenate them. So you can see down here that I have this lift operator, this lift that is taking some x. So my type here, my class numeral is parametric in this notion of x. Don't worry about all this right now. And what I'm saying is that I can lift whatever object x that I have into my new grammar, or I can concatenate two objects that I have into my grammar for long numbers. And then I said, okay, now I need the notion of what adding multiple numbers together might look like. So I said, all right, let's define yet another grammar, which has sum, which can either be like a numeral here, or it can be two sums added together. So again, I had this notion of lifting. This is another like parametric thing that is going to take this notion of numeral, and it is going to have both this lift grammar construction and this add grammar construction that takes two sums, and the lift notion takes whatever item we're parametric in. So then I thought, okay, so starting from this sum object, let's sort of start filling out a little bit and defining our equivalences. So I realized that really, if I have a plus b or b plus a, I want to be able to express those as the same thing. So I thought, okay, my class sum, really the thing is that we care about is we care about storing a multi-set of these x's, a multi-set of these numerals that are all added together. And so I put that multi-set in there. I then went down here and said, okay, so in my lift operation, all I really need to do is define a new multi-set which only has the object x in it, because we're not adding two things together yet. It's just one number. Or if I'm adding two things together, I need to put whatever is in the multi-set of I need to add together those two sum objects. So I just need to put, I need to merge those two multi-sets together to create this new multi-set that has the objects in both. And then I thought, so that was kind of neat. And then I thought about defining the reductions. So for this language, I'm thinking that the reductions are what you do is you just take a number, and one reduction step is taking one number and adding it to another number in your sum and returning whatever you get. So I said, okay, so what I have to do is I have to sort through my set of, or I have to iterate through everything that's in my multi-set, because I'm giving actually the whole, I'm not only finding one reduction, I'm finding the whole set of reductions here, returning from my reductions here. So I iterate through everything in my sum, and then I iterate again through everything in my sum minus the first thing I pulled out. And what I'm going to do is I'm going to yield a new sum, which has my initial sum minus the two things that I'm adding together, because those are going to equal a new thing, and then plus this sum and a plus sum and b. So then I needed to realize that I needed to, since I wanted to sum and a, add sum and a and sum and b together, and these are the things that that I'm parametric in, what I need to do is I need to say, okay, these things, I can't really just take any object to be, for my sum to be parametric in. Those two objects that I take have to be addable. They have to have some notion of addition to them. So I define this new trait addable, saying that we have something that takes an x and returns an x. And I'm saying that I'm requiring that x implements addable, so that this statement here will compile. But then now I've just pushed a requirement onto my numeral type. So I went back up here and I said, okay, so now I need to make sure that my I need to make sure that I extend some dot I extend some dot addable with my numeral class. And then I just sort of went up from there. So that pushes some requirements back down to digits as well, that they're addable. So I don't quite like yet how I've decided to push those notions back down. I've sort of given them in a little bit fuzzier of a manner that I would like, that doesn't really treat the class of object that is below our current class definition as something that can contain computations itself. I'm just sort of saying, I'm going to push some requirement on you that like you reduce and give me this. So, and then yeah, we could go. It gets into the weeds a little bit here because my numeral class is doing some fun stuff where it's taking, it's taking a number ring and it's doing addition of just the digits. And then since I'm returning a digit, I can't return like 9 plus 1 can't equal 10. So I have to, I've defined it as like I'm doing modular arithmetic for the digits is my sum. And then at this level, what I'm doing is I'm checking for overflow essentially in this modular arithmetic, and then using my concatenation tool that I have defined at this level of numeral plus numeral to define a new number which carries the ones essentially. But for that notion, I force this definition of the one back down to the digits. So that's what I was doing.
And this is the place where you combine digits in like a new, bigger digit, but yep. not sum, but like a combine.
Yeah, exactly.
In here. And very distinct, like a 0, 1, and 1. 0, 1 is equal to 1. Right.
Yeah, so I do that. Actually, I think, let's see if I just maybe did that this morning, and I don't know if I pushed it or not. No, I think I did. So that would be here in my concatenation. So this is where I do it here. So I check to see if so I'm concatenating A and B. So if A is 0 and B is 1, what will happen is that we'll see that. So I also did some funny stuff here so that unary would work. So that in the mod 1 ring, 0 is our smallest object, which contains value, and then it's just the number of zeros is what your number is. So I made these classes such that I work with unary as well. But anyways, so what I'm checking here to make sure that this number, if A is 0 essentially, then I just return the B number. Otherwise, I add the sequences together of the numerals of B and numerals of A.
I'm wondering, but when you have addition as operation, then well, I wanted to like save all the zeros for structural equivalence, and if you're adding two numbers that have, this other number have 0, you want to like remove the zeros, or like say this is not important. And
yep, yeah. So that's what I'm doing here. That's what I'm doing here. So yeah, my my class numeral x is basically the only thing that matters in equality is the sequence of x's, which are my digits. And what this is saying is that if you can't even construct a number that would be like 0002 unless you are using. Unless you are in unary, then you can construct the number 0, 0 plus 0, 0, 0, because that's 2 plus 3 in unary. So, yeah, do you want to show your?
Oh yeah, sure.
Talk about your solution.
Yeah, I have I also don't have a complete solution. The final step I didn't. Yeah. So let me see. So share screen. Sorry, I don't see my. Oh, it's here. Do you see my screen?
Yep.
Okay, great. Oh, I can zoom in. No. I don't see that. Okay.
Yep.
It's very slow.
That's readable.
So this is like a definition of digits. I only have one like a semantics, and this is the definition of combining two digits, and this is like an addition. And I have different implementations. I first started with like a completely shallow embedding, and just each of the language rule is just an integer. But in this case, I don't have any like a structural equivalence is identity, and evaluation reduction is also evaluation. I mean, without immediately when you construct the language, I made all the reductions. So this is like a good example that I understand how I don't have like a rich structure that I can introspect. I have only integer at the end. So I add additional structure just to have these digits combined in a list. And in this situation, I have different structural equivalents. And it's visible here. So this is like a construction of 11, and it's structurally equal to adding 10 to 1, and this is true. But in a second case, this is not structurally equal, because here is adding, and here is just combining two numbers. So I'm not sure. Yeah. And for this equality, I'm not sure is this alpha equivalence, or because this is after all reductions. After all reductions, these two implementations are the same, but in structural equivalence are not the same. So I still don't know what is the right thing to do. But so in the third step, I wanted to have also the addition to be like a structurally different, and I also choose the multiset to combine these two things. But I didn't finish the structural equivalence and reductions. So
Cool. That's neat. Yeah, that looks a lot different than what I did.
yeah, but I looked your examples on in Scala on row calculus. So yeah.
Cool.
Because from there, I somehow understand that I need some kind of richer structure to memorize all of these different different rules in semantics. Yeah.
Yeah. Awesome. Can you send that link in the chat for me?
Oh yeah, it's on my GitHub.
Okay. Structure rolling HS. Okay. Cool.
Yeah, that's it.
All right. Yeah. Great. Thanks. Cool. Does anyone else have any questions, or what questions do you have? Hello. Sorry about that. Just crashed. But OK. Anyways, thanks, everyone, for joining today, unless there are any other questions. And see you next time.
All right. Take care.
Thank you, Jake.
Bye.
Goodbye.
Okay.
Bye.
Yeah.
Bye.
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 Bye. Bye.